Okay, so this is the third online Horowitz seminar meeting. Thank you all for coming. And we're very happy today to have Nathanaël Berestycki from the University of Vienna, who will tell us about random walks on planar maps and Liouville Brownian motion. Thank you for coming, Nathanaël.
Okay, so hi everyone. It's wonderful to be here. I have to say, I wish I could be in Tel Aviv in person. So this will have to do.
We'll be very happy to have you as well for a visit.
So, but by the way, it seems that most people can hear me, except one person is saying on the group chat that they cannot hear me. So I hope that they were able to fix their issues. If there are any technical issue or if there is any questions, then please feel free to interrupt and ask questions. Otherwise, it's very hard to know whether, first of all, the audio is coming out okay, the video is coming out okay, and the kind of what I'm trying to say is comprehensible. So I will tell you about some recent work on the subject of random walks on planar maps and Liouville Brownian motion. So this will be the result that I will say is joint work with Ewain Gwynne from Cambridge. I will get to it towards the end of the talk. First of all, I will try to give you a bit of introduction. Sorry, the bottom of the slide is a bit hard to read maybe, but it's not very complicated, so I will say it. So word of motivation, this starts with the remarkable paper of Benjamini and Schramm from 2001, where they asked the following question: what does a random walk look like on a random planar map? And the kind of planar maps that they had especially in mind when they wrote this paper is the so-called UIPT, the Uniform Infinite Planar Triangulation, which was introduced roughly around the same time by Omer, Angel, and Oded. And what this is, it won't really be relevant for the rest of my talk. So I won't spend much time explaining what this is. Probably many of you are aware of it, and that's great. And if you're not aware, it's not so important for the rest of the talk. But it's the sort of maps that are described on this picture that you can see on my slide here. And what this is the local limit of randomly chosen triangulations with n faces as n tends to infinity. This way, you get an infinite triangulation in the plane, and with an it's an infinite graph, and this is called the UIPT. And their motivation for considering this came from physics, and in particular work of Ambjorn and Watabe, roughly around the same time, late 90s, non-rigorous work, which claimed that, I put this in quotation mark here, that the spectral dimension of Liouville quantum gravity was 2, almost surely, meaning that if you were to do, so one way to phrase this is that if you were to do a random walk on this sort of infinite UIPT, this infinite planar triangulation, and you ask yourself, what's the chance that the random walk is back to its starting point at time t, then this decays as t tends to infinity, like it would on the two-dimensional Euclidean lattice, meaning like 1 over t. So this is what is meant by the spectral dimension in 2. And so, 1 over t, of course, when you sum it, you get something infinite. And so this led them to conjecture that, in particular, the UIPT is recurrent. And they proved the following result, that in fact, if you have a sequence of planar maps with bounded degree, so this was their assumption in the result, so subject to bounded degree, every local limit of a sequence of planar maps is recurrent. And this was very strong evidence that the UIPT itself is recurrent, so this was very consistent with their conjecture. And in fact, the assumption of bounded degree was removed in a celebrated paper of Ori Gurel-Gurevich and Asaf Nachmias, and showing that you can change the assumption of bounded degree for one on the tail of the degrees, and then an exponential tail on the degree suffices. And so this talk won't be about recurrence of random walks on planar maps. This talk will be about scaling limits of random walks on planar maps. And but if you're interested in this topic, then of course you can go and take a look in Asaf Nahmias' lecture notes on the on this topic in Saint-Flour, from his Saint-Flour note. So as I said, my talk will be about scaling limits of random walks on random planar maps. And I have two things that I need to do. One is to introduce the object that is the candidate for scaling limits. So that will be the Liouville Brownian motion from my title. And the second is to try and tell you the kind of random walks for which we can prove scaling limits. This will not include the UIPT. And that's why you don't need to know about the UIPT for my talk. But they include things that are called mated-CRT planar maps, which I will try and describe. And then I will get to the stating the result and hopefully tell you a little bit about the proof. But that's a lot of things to cover. And it may be that, I probably will try to be more impressionistic than give you every rigorous details. Still, if what I'm saying is confusing, then please try and ask questions, and I'll do my best to answer. So let me tell you first of all a bit about the possible scaling limits. So in order to do that, I need to tell you about what's called the DDK Ansatz. So this was something that came from physics, but was explained to the probability community largely through famous work of Bertrand Duplantier and Scott Sheffield, roughly a bit more than 10 years ago. And they explained that the geometry associated with the UIPT should be related to a random geometry in the plane, where the metric takes the form of e to the gamma h times the standard metric. Now, what does this mean? So here, first of all, gamma is a parameter. It will be equivalent to the what the physicists call the central charge, or what in SLE we call the parameter kappa. So gamma is just a parameter if you want. H is going to be the Gaussian free field. I'll say a word about this. And roughly, what does e to the gamma h times, what does it mean to say that the metric is e to the gamma h times dx squared plus dy squared? One way to think about it is that very informally, we have a metric, a random metric in the plane, where if I draw a ball of Euclidean radius, of Euclidean area epsilon in the plane, then it corresponds in this random geometry to a random area of size e to the gamma h times epsilon, where h is a Gaussian free field. You can think that this is a region in which if I go back to the previous slide, then the number of triangles, the triangles are packed very, very closely together when h is very high, and the number of triangles is proportional to e to the gamma h times epsilon. Okay, so that's one way to think about what is the meaning of this identity here. Now, what is the Gaussian free field? You should think of the Gaussian free field as a random function from some given domain into the plane. Function I put in quotation marks because actually it's not pointwise defined. So what is well defined are averages of the Gaussian free field when you test it against some nice test function f. And then by definition, what you get is a Gaussian random variable with mean 0 and variance sigma squared. And sigma squared is given by a double integral of the green function against f of x, f of y. So, another way to read this definition, what does it mean? It roughly means that the Gaussian free field, well, it's not pointwise defined, but if it was pointwise defined, it will be a Gaussian if you were to able to test it to look at its values at point x1, x2, xn, you get a multivariate Gaussian distribution whose mean was 0 and whose covariance would be given by the Green function.
Nathanaël, a quick question.
Yes.
You mean a real function, not a complex?
Yes. Oh, that's a typo here.
Okay.
Thank you.
I wanted to make sure. Yeah. Okay.
Thank you. Yeah, it takes values into the real numbers. So that's a typo. Thank you, Ofer. I really mean the real Gaussian free field here. And right, so I was about to say that the Green function, of course, blows up in 2 dimension on the diagonal. So when y tends to x, then the Green function gxy converges to infinity. And that's another way to say that the variance at a point is not well defined, because you cannot look at the Gaussian free field at pointwise. You cannot not look at its pointwise values. Okay, so we know what is the Gaussian free field H, but it's really not clear what exponential of the Gaussian free field means. If you think a bit about it, the fact that you can assign values to local averages of the fields just means that there were lots of cancellations between plus and minus infinities all over the place, so that when you test it against a function, you get something that's finite. And it's not clear at all how that translates when you try to take the exponential of the Gaussian free field. So a priori, if you try to assign a meaning to this expression that comes from physics, it's not clear how you can do that without saying what it means. And a priori, there's sort of 3 objects that one might care about. There's a metric that's the first of this. Maybe that's the most natural. The metric would be obtained by, at least intuitively speaking, considering lengths of curves where you integrate along the curve e to the gamma h along the curve, so that you get a random length each time you do that. There is a volume measure where you assign an area which is random to any given set, and the area is informally obtained by integrating exponential of the Gaussian free field on that in that domain. And the third object, which will play a role in my talk, is the diffusion, the notion of diffusion, the natural notion of diffusion, which informally speaking is given by this SDE here. So I won't tell you much about the metric, because anyway, that's the most distinct from what I wanted to tell you about. But we're now in a situation where we know how to construct the metric, even though it was in fact the last of these 3 objects to be defined properly. And this was announced just last year in a sequence of 6 papers, all of which were published on the same day on the archive. That was amazing. 5 by Ewain Gwynne and Jason Miller, and the 6th one by Julien Dubeda, Hugo Falconet, Ewain Gwynne, Josh Pfeffer, and Shin Sun. And for the special case of the value gamma equals square root 8/3, actually this value plays a special role in the theory. In this result, the fact that the metric, there was already a metric, this was known from earlier results of Jason Miller and Scott Sheffield. So I will tell you more both about the volume measure, because it's the easiest to define, and about the diffusion, because that's the one I care about for this talk. Please feel free to interrupt if there are questions at this stage. So let me tell you about the volume measure, because the Brownian motion construction will be somewhat similar. So to define a measure, what we do is, well, we don't know how to take the exponential of the Gaussian free field because it's not pointwise defined. So what we do instead is we take some regularization of the Gaussian free field. It could be the circle average value of the Gaussian free field at distance epsilon from the point Z, but it could be something else. So some modification of the Gaussian free field. So that gives you something that is pointwise well defined. And then there's no problem in exponentiating that. And so that, you can view this now really as a random measure. And if you rescale it appropriately, you can hope that this will converge, this will have a limit as epsilon tends to 0. And so this is something that we now know very well. This procedure is called the Gaussian multiplicative chaos associated to the Gaussian free field. And it goes back to many people. Really, I should for sure mention the work of Jean-Pierre Cahan in the 80s, who did this in a somewhat slightly different form, but really it boils down to this. And this was rediscovered by this work of Duplantier and Sheffield from 2010, I've already mentioned, and in this form that I'm mentioning also relates to a theorem of Shamov and to myself in 2017. So this is the procedure for defining the area measure associated with the exponential of the Gaussian free field. So here's some nice simulations due to Rémi Rode. What this shows is basically, is there a question? Sorry? No. So what this shows is basically a plot of the density when epsilon is still positive. So when epsilon has 10, after you've taken a limit, the measure that you get does not have a density with respect to the Lebesgue measure, but before that there is a density, of course. And this can give you a sense of what this measure looks like. And this is a plot of this density for gamma equals 0.2, so very small. And you see that the measure is already very spiky and very irregular, even though when gamma is small, we should have something that's very close to the Lebesgue measure. And then when you increase gamma, then you see that this effect becomes more and more pronounced, and you have a measure that's more and more spiky, and you get close to the value gamma equals to 2. It turns out this is the critical value after which the measure degenerates to 0. But for any gamma that's less than 2, there is really a measure about which we know a lot. And the bigger the gamma is, the more this measure is singular with respect to Lebesgue measure. Okay, and now I want to tell you about Liouville Brownian motion, which is in some sense the main topic for this talk. And the question is, how would you define a canonical notion of Brownian motion in this random geometry? Now, if you're doing Riemannian geometry, then there is sort of a standard recipe for producing a Brownian motion on the surface or on the manifold. And really the way this goes is that the metric defines a connection, so something which allows you to differentiate functions on your surface. And once you have that, there is a notion of Laplacian. And then the Brownian motion is just defined in terms of Laplacian. It's the process whose generator is given by the Laplacian. So of course here, none of these tools apply because differentiating function is not going to work in this very sort of fractal context. So you have to do something else. And this is what I did. So there were two papers appearing despite different publication dates in 2015 and 2018. There were two papers that appeared basically on one day apart on the archive, one by myself and another one by Christophe Garban, Rémi Rode, and Vincent Vargas. And the idea is to, again, do a regularization procedure. And what you did, so, as I said, the natural thing principle is given in terms of an SDE, which is just saying that the infinitesimal increment of your process should be proportional to that of a Brownian motion, but amplified by a factor e to the minus gamma over 2 times the value of the Gaussian free field at the point where we're diffusing. And again, to give a rigorous meaning to this, you have to consider a modification of the Gaussian free field. And the appropriate way to normalize turns out to be given by this factor here, epsilon to the gamma squared over 4. And the theorem is that if you do that, then as epsilon tends to 0, this epsilon regularized Liouville Brownian motion really has a limit. And another way to put it is that, and that's really an equivalent description, is that you can start with, oh my God, I'm sorry. you can start with some Brownian motion in your domain, some Euclidean Brownian motion, and all you're going to have to do is time change it. So you're going to introduce this clock phi epsilon of t, which is simply the integral from 0 to t of e to the gamma times the regularization of the Gaussian free fields at the point B where your Brownian motion is running, integrated against time. And you normalize it appropriately, and you use this clock to time change your Brownian motion. So the value of the Brownian motion time s will just be the regular Brownian motion time changed by the inverse of this clock. And then the theorem says that as epsilon tends to 0, there really is a limit uniformly on compacts when you do that. So in order to give a feeling for what this diffusion is doing, I have a video that I like to show. Now, we can in principle share video on Zoom, but the video does not show very well, does not show very smoothly. So what I'm going to do is I'm going to share a link to the chat, and it's a YouTube video. So here I've just sent it. Everyone can click on it and can look at it. Those of you who will be watching on YouTube later, there will be a link to this video somewhere in the description. And I encourage you to click on it. So this is a link that you should have received by the group chat. And I will do that myself, actually. I will look at this video. And what you see on this video is several things. There is a green landscape, which is, well, a regularization of the Gaussian free field. And you see on top of that a particle moving. And what this particle does is a sample from a Liouville Brownian motion in this realization of the Gaussian free field. And so you can play it again. I don't know if you've noticed what happens, but if you watch this video, you will see that one of the things that is quite striking about it is that the particle spends quite a bit of time, on top of mountains somehow when the field is very high. And it's important to understand why that is. So it's not that somehow the particle is attracted to the top of the mountain. That's not that. The particle is isotropic. If you look at the definition, if you go back to my slides, if you look at the definition, you will see that it really is just a time change of Brownian motion. So it's not that it has any preferred direction. It does not prefer to travel towards places where the field is high. It is isotropic, but when it finds itself in position where the field is high, then it just slows down a lot. And so what you see is Liouville Brownian motion spending a lot of time in places where the mountains are very high. And somehow this corresponds to the fact, if you want, that the area that is represented by this region is in fact very big. And so it should really take Brownian motion a lot of time to get out of this region. And that's why it's going down. Another way to put it is that, if you think in terms of the discrete process, we hope that this represents a region where there's a lot of triangles. And so it takes a lot of time for random walk to get out of this region. So I hope this gives you a feel for what it is. Liouville Brownian motion is just this Euclidean Brownian motion, but time change through this singular time change involving the Gaussian free field. So there are several things that we know about it. We know, for instance, that the trajectories are almost surely continuous and don't stay stuck. So this may seem kind of obvious maybe, but in reality, when gamma is high, the mountains could be so high that your Liouville Brownian motion just likes to hang out so much at these mountains and just never leaves. And in fact, when gamma becomes greater than 2, in some sense, this is what happens. Things degenerate and Liouville Brownian motion never leaves out of these mountains and there's nothing to see. We do know that the Liouville measure that I introduced before is almost surely invariant for Liouville Brownian motion, and that's a good indication maybe that we're looking at the right diffusion. We know, for instance, that it spends all its, when I say all its time, Lebesgue all of its time in a set of measure 0. That corresponds to places where the Gaussian free field is exceptionally high. And so it spends a lot of its time there, even though it measures very little in terms of Lebesgue measure. One property that's very surprising for probabilists the first time that you see that is that when gamma is greater than square root 2, so remember the phase where it's well defined is gamma between 0 and 2, it degenerates after that, but gamma can be greater than square root 2. And you get something non-trivial when you do that. So for gamma greater than square root 2, then the trajectory has almost surely 0 derivative at almost every time. And so somehow, you know, the mountains are high enough that the process kind of wants to stay stuck at almost every place, but still lives, right? So the mountains are not high enough that the process stays stuck there, but high enough that the derivative is almost every time 0. Right, so it really is a very singular time change. And one thing that we do know about this process, and that verified in some sense the conjecture, the prediction by Watabiki and Ambjorn, that the spectral dimension is 2 almost surely. This was proved by Rode and Vargas. These properties, I should say, that they were proved in several different papers. So this is really a summary of things that we know, and we know a lot more than what I've been able to write on this slide. Okay. So I want to tell you a bit about connections between the discrete and the continuum side of the story. What do I mean by that? I mean, I want to try and say something about scaling limits of random walks on planar maps and connect it to this notion of Liouville Brownian motion. And the first thing I need to do is to tell you how to embed the planar maps. And of course, you know, there is a good reason why I need to tell you that, because of course, you know, Liouville Brownian motion refers to specific positions of points in space. But you know, random planar maps a priori, they are combinatorial objects and don't come necessarily with an obvious way to embed them in Euclidean space. So there are many ways to do that. Many people like to use maybe the circle packing theorem. In fact, last week's Horowitz seminar was about circle packing. So I won't do that. So I won't tell you about circle packing this time around. Another way that's very nice is using the Riemann mapping theorem or the uniformization theorem. And another thing that you can do, which may be more relevant to my talk, is the notion of Tutte embedding. So this is something that you can do when you've got a graph with a boundary. So if your map is finite rather than infinite. And so what is the Tutte embedding of a planar map with a boundary? So it's just a drawing of your map in such a way that random walk on this on your planar map will by definition be a martingale. So in other words, what you do is just you draw your graph in such a way that every vertex has a position which is the average of the position of the neighbors. So it's not very complicated to do that. If you've got a graph with a boundary, then you can start by fixing the position of the boundary vertices anywhere you like. So let's say on the unit circle, for instance. And then what you can do is you kind of solve the Dirichlet problem on your graph with this boundary data. And then, of course, you know, by definition, you know, the position of the vertices will give you a harmonic function on your graph. So, so by definition, the position of the random walk on this embedded graph will have the property that it's a martingale. Now, what is quite remarkable and what is what Tutte proved about this is that if you also draw the edges of the graph in a straight line manner, using straight edges, it turns out that you get a planar realization of your graph. So that's not at all trivial. And that's the content of the theorem. So the edges can be parallel to one another, but they cannot cross one another. And so this will be a planar realization of your graph. So you can keep this embedding in mind because that's one of the embeddings for which our theorem will work. But this is an embedding that makes sense when your graph has a boundary. And when your graph is infinite, I will use a different kind of embedding actually, which I'll tell you more about, and it comes from the specific definition of the map. So here's maybe the kind of conjecture we're trying to talk about here. If you've got, let's say, uniform random triangulation and psi some nice embedding of the triangulation into the complex plane, could be circle packing, it could be Tutte, it could be something else. Then the conjecture says the following: you can put mass 1/n at each center, by center I should say, at each vertex drawn into the plane. And the conjecture says that as n tends to infinity, this should converge basically to a variant of Liouville measure with parameter gamma equals square root of 8/3. So I've already said that this parameter plays a special role in the theory. And moreover, if you're performing simple random walk on this triangulation and you look at how it moves once you embed it into the plane using your nice embedding psi, then the theorem, no, not the theorem, the conjecture is that as n tends to infinity and after rescaling, you should converge to Liouville Brownian motion, again with the same parameter gamma equals square root 8/3. So I can tell you the punchline of our work that I've been trying to advertise since the beginning. So this is joint work with Ewain Gwynne from Cambridge, as I said. And this is the first work in which such a result is obtained. The class of planar maps for which we can prove this result are called mated-CRT planar maps. I will now tell you about those. And there are sort of two nice ways you can think about them. They are actually quite different from one another. So one way is as a very nice discretization of Liouville quantum gravity. So they are sort of maps that are, it's a class of planar maps that are as close as you can hope for when you try to prove a result of convergence of discrete planar maps towards Liouville quantum gravity. They are sort of made to be close to Liouville quantum gravity almost by definition. Nevertheless, proving convergence result is often quite challenging. And on the other hand, there's another way you can describe them that's, I think, is why they're interesting. This reason is simply that you can view them as coarse-grained versions of more natural models of planar maps, including the UIPT in the case gamma equals square root 8/3. And what I should say is that, so sometimes the way this is a coarse-grained version of these models of planar maps means that you should expect to be able to relate these models, this more natural model of planar maps, to these mated-CRT planar maps. Sometimes you can do that rigorously, and sometimes this connection is strong enough that results that you prove for mated-CRT planar maps can be transferred for the more interesting models of planar maps, more natural models of planar maps, such as the UIPT. That's not yet the case for the results I'm telling you, but it's not out of the question that at some point this will be possible. So let me tell you a bit more about these mated-CRT planar maps. We prove our results in two different cases. One is a finite case with a boundary corresponding to the case of maps with a topology of a disk, in which case we'll be able to do a Tutte embedding, so a very interesting, very nice kind of embedding. Or the maps can be infinite with no boundary, having the topology of the sphere or of the plane if you want the whole plane. It's the same thing. So the result is going to be true for both of these situations. And in both of these situations, these planar maps can be described in two equivalent fashions, corresponding, roughly speaking, to these 2 points of view that I just tried to mention. So one in which there is a description which allows you to relate this map directly to Liouville quantum gravity, and one with a description that allows you to relate this to more natural models of planar maps. So the first description is the one that uses SLE and LQG theory, Liouville quantum gravity theory. That's probably the easiest one to explain. So that's the one I'm going to give. And I'm not going to say much about the second description because it's kind of harder to wrap your head around in a talk of with just a few minutes to speak about. But in some sense, that second description is the one that's more interesting for trying to relate things to a more natural model of planar maps. The fact that these two descriptions actually describe the same object is very far from trivial. It's a consequence of some deep relations proved by Duplantier, and Sheffield in their paper called Liouville Quantum Gravity as a mating of tree. Okay, so let me tell you about the first of this description, which has to do with SLE and LQG, so Liouville quantum gravity. So we're going to start with fixing a parameter gamma in 0 and 2, between 0 and 2. Maybe I've so far insisted a bit more on the value gamma equals square root of 8/3, because that's the one that should correspond to the uniform infinite planar triangulation, the UIPT, but actually our results are true for any gamma between 0 and 2. And to describe the planar maps, these mated-CRT planar maps, I need two ingredients. The first one is what's called a quantum cone, and the second one will be a version of SLE. So what is a quantum cone? Roughly speaking, it's a variant of the Gaussian free field. I'm simplifying things slightly, but not very much. So it's what it is, roughly speaking, is a version of the Gaussian free field in the full plane, to which you add a logarithmic singularity multiplied by gamma placed at the origin. So it's a Gaussian free field-like object, if you like. So that's the quantum cone. And the second ingredient is an SLE kappa, where kappa is the parameter 16 over gamma squared. So because gamma is between 0 and 2, gamma squared is between 0 and 4. So 16 over gamma squared is between 4 and infinity. And if you know a bit about SLE, then you know that this corresponds to the range of values where the parameter kappa, so the parameter kappa corresponds to the range of values where the curve is not simple. So when kappa is between 4 and 8, the curve can touch itself, but not cross itself. Whereas when kappa is greater than 8, then actually the curve is space filling. And the curve eta here that I want to consider is a space filling version of SLE. So when kappa is actually greater than 8, then SLE is already space filling and there's nothing to do. So eta is really just a regular SLE curve. Whereas when kappa is between 4 and 8, you need to modify it. You need to modify the definition a little bit because you have to say that every time SLE completes a loop, then it's going to go and visit things inside the loop before coming out. So there is a well-defined recipe of turning SLE into a space-filling curve. This is a non-trivial work. It was done by Jason Miller and Scott Sheffield in their investigation of what they called imaginary geometry.
Nathanaël,
yeah.
Question regarding the quantum cone, similar to Offer's question, you have logarithm of 1 over z, and that's a complex number, so h is now complex valued? Or is it that you put absolute value somewhere?
Yes, excuse me, it should be log 1 over modulus of z. So it's the real part. I've just noticed that I've missed some questions on the chat. You do well to interrupt me Ron, because, okay, so Asaf had a question way before. I answered them already. Okay, thanks, Asaf. I'm sorry. For some reason, the chat window was not showing up on my screen until now. Thank you for forgiving me. Yes, so indeed, so the Gaussian free field should be, the quantum cone should be just a Gaussian free field in the full plane plus gamma times a logarithmic singularity at the origin. So there's a modulus missing from the log. Okay, so we've got these two ingredients, the quantum cone and the space-filling SLE curve from infinity to infinity, or this is what you would do in the full plane. And so the way to get a graph from these two ingredients is the following. We're going to fix epsilon strictly positive, and that's going to be like the mesh size of the graph, if you like. And we're going to break the complex plane into cells. This is intervals of time. So this is regions of the plane covered by the SLE in an interval of time, tn plus 1, such that the area of that region is by definition epsilon. And by area, I mean area measured according to the Liouville measure associated with this quantum cone. Okay, so because this H is basically a version of the Gaussian free field, you can make sense of the Liouville measure associated with this random field. And so that gives you a way of breaking up the planes into regions of size epsilon. So roughly speaking, I think this picture is supposed to show you some of this construction, where you see a bunch of cells. In fact, the colors are representing, I think, something like 100 cells or something like that. So just to be clear,
again,
yeah.
is the quantum cone and the SLE kappa, the space-filling SLE kappa, independent?
Yes, they are independent. Thank you.
Okay.
So they're independent from one another. Sorry if I didn't say that earlier. And we are breaking up the plane into regions, all of which have a mass of size epsilon. And these regions have a complicated geometry. They correspond to, they have a fractal-like boundary because they are sort of SLE-like curve on the boundary. But nevertheless, because the SLE space-filling have completely split up the plane into regions, each of which have a mass epsilon by definition. Is that clear? I've done this procedure. So associated with these cells is a graph where you just put a vertex at the center of each cell, and you declare that two vertices are adjacent if the corresponding cells, they are adjacent to one another, they are tangent to one another. Okay, so there's a graph associated with that, and you can see how this graph is made to be very close to Liouville quantum gravity already from its definition. Okay, it's a bit like maybe an analogy would be if you are trying to describe discretization of a one-dimensional Brownian motion, and instead of looking at uniform walks with plus or minus 1 jumps, you were to consider a Gaussian random walk, so a random walk where the steps are Gaussian. It's a bit like you were trying to discretize your Brownian motion by considering its values at integer times, roughly speaking, is what I'm saying. So these planar maps, they are very close to Liouville quantum gravity already from their definition, basically. So that's why they're the most natural candidates if you try to prove a scaling limits result about random planar map quantities to Liouville quantum gravity. So as I said, there's a second description, which is much more involved, but in some sense is the more interesting of the two descriptions. And that this is the description which allows you sometimes to relate rigorously this planar, this mated-CRT planar map towards interesting models of planar maps, or more real, more natural models. And the way this description works, just in 2 words, is by taking a pair of correlated Brownian motions. So you just take L and R, a pair of correlated two-sided Brownian motion, infinite Brownian motions, where the correlation coefficient is given by this quantity here, this strange quantity, this minus cosine of 4 pi over gamma squared. I know it's a weird number, but that's the way it is. And the thing is that both L and R can be used to encode continuous random trees associated with their trajectories. So, I won't go into that because it would take me way too much time to try and describe that. So if you know what that is, great. And then the idea is to sort of glue these trees together by identifying the points on the tree at time t, corresponding to the time t on the L tree, to the points at time t corresponding to the R tree. So this is a way of gluing two trees together, and this is a topological gluing, and it turns out that this then has a topology of a sphere, and you can use that to define your planar maps somehow. So I don't want to get into that because that's a much more involved description. If we had 15 minutes more, maybe I could give you a description, but I think in this situation, it's best to sweep this under the carpet. Nevertheless, it turns out that many natural models of planar maps have a description that is very close to that, that is provably very close to that, in the sense that they are described by gluing of discrete trees, which can be proved to converge to these continuous random trees with the correct covariance coefficient. And the way often the constructions that allow you to do this, to prove this relation, goes via bijective techniques. There are various bijections, in particular those introduced by Scott Sheffield. His hamburger-cheeseburger bijection does that. And in some sense, going back to work of Bernardi and Mullin, and more recently of Holden and Son. And so these bijections allow you to relate, to give a description of this, of maps in terms of gluing of trees, which are close to this thing that I've just mentioned. Anyhow, so we've got these two ways of speaking about our planar maps that are very different from one another, but nevertheless equivalent. That's the work of Duplantier-Sheffield. And I can finally state my result. How much time do I have at this point?
You have 12 more minutes.
12 more minutes, okay. So I'm going to state it in the case of the full plane for simplicity. So I'm going to consider this mated-CRT maps that I've described in the full plane. So with my quantum cone and on top of that, space filling SLE and breaking up the plane into cells of mass epsilon. So this gives me a graph, and I can consider X epsilon will be the random walk starting from Z, or a vertex closest to the point Z, on this graph G epsilon, and then linearly interpolated. And I want to rescale time. So what I'm going to do is I'm going to rescale this by parameter M epsilon. So this is such that by definition, the time for this random walk to leave a macroscopic region, for simplicity, we take the Borel radius half around the origin. This is, okay, could be something else, doesn't matter. And so we rescale time so that by definition, it will take of order 1, the median time to exit a macroscopic region will be of order 1. We can show that M epsilon will be of order 1 over epsilon up to constant. So the theorem that I wanted to advertise, so this is in a paper that you can find on the archive. It was put on the archive last week. And the theorem says that for every Z on a complex plane, the conditional law of the embedded walk, so it's embedded using this SLE embedding. So eta is the SLE curve. And so the embedded walk, using the SLE embedding, you speed up time so that it has this property that the median time to leave a macroscopic region is of order 1. You condition given given the Gaussian free field and the SLE curve, then the law of this random walk converges as epsilon tends to 0 to Liouville Brownian motion with parameter gamma starting from Z. So I've stated here the result in the full plane case, but actually there is also a result in the disk case, in which case we can actually use the Tutte embedding for the planar maps, which is a more canonical embedding.
Nathanaël, can I ask a question? So the limit does not see eta, even though it's conditioned on eta.
Yes, that's right. That's right. So if you want your map, you have the choice to embed it either using Tutte embedding if it's available to you, or using the embedding that comes from SLE LQG theory. So I should say I've insisted on the fact that we have 2 equivalent descriptions, but the description number 2 is a sort of combinatorial description. It does not refer to a particular embedding. It's a topological gluing of trees and does not come with a natural embedding a priori. The fact that it's equivalent to description number 1, that one really comes, here vertices actually have a position that is prescribed in the plane that comes from the SLE curve. Does it make sense? So
sort of, except I would be less shocked if you told me that the annealed law is the
yes,
same. But here you are saying that even if you condition on the embedding.
Exactly, because really, you can imagine take this graph here, okay, even the one that's embedded, and now consider the Tutte embedding of that. So that has nothing to do with the with eta anymore. It's embedded using the Tutte embedding, so it's an intrinsic description of the graph. If I give you just the graph, I can embed it using Tutte embedding. Then the theorem says that the position of the random walk embedded using Tutte embedding converges to Liouville Brownian motion with parameter gamma. And the reason is that the Tutte embedding and the SLE embedding, they are the same in the limit. Does that make sense, Ofer?
They are the same, so maybe I misunderstood what they are the same means. They are the same actually deterministically or in law? They
are the same in this sense exactly. So I was going to say it. So if I take the graph, I can embed it using eta, that's the SLE embedding, or I can embed it using psi, that's the Tutte embedding. And the previous work that we have from this is a paper of Gwynne, Miller, and Sheffield, shows that actually these 2 embeddings are the same in the sense that they are uniformly close to one another.
Okay, thanks.
Yeah, so I think this is not an easy point to understand maybe in a few minutes. Maybe it takes time to, but you've got this graph, this abstract graph, and a priori, there's sort of 2 ways I could embed it in the plane. One is with using SLE theory. That's actually one way of defining these maps, maybe the easiest way of defining these maps. And the other one is to apply some nice embedding, intrinsic embedding, like the Tutte embedding. And the theorem, let's say in the disk case, says that in both cases, the position of the random walk, let epsilon tends to 0, will converge to gamma Liouville Brownian motion. Okay, and I think if I can do it for Tutte embedding, you should not be surprised that I can do it quenched with the SLE embedding. Does that answer your question, Ofer?
Yes, it does. Thank you. There's also a question in the chat if you look at it.
Thank you, Matan. Is the speed up you use here the same speed up with okay, no, this is just thank you, Matan, for asking this question. The question is what is the speed up here that I'm doing? So I've just done a linear rescaling of time here. I speed up t by a factor. You should think really that I've divided t, but it's like t divided by epsilon. Thank you. So it's great that you got it. I will still explain this because this is interesting. We were hoping initially to prove the result with time t rescaled by 1 over epsilon rather than this median, but it turns out we could not prove the result in this way. We can prove that is because there is a constant that we cannot identify somewhere. And so we find a way to, maybe it will become apparent, a bit more apparent once I explain what is the method of the proof. So one workaround was to rescale by this fixed quantity. This is the median of the time needed for the embedded walk to leave a macroscopic region, this ball of radius half. And we can show that up to a constant, this looks like 1 over epsilon. And we very much believe that the same result is true if I rescale time t by a factor 1 over epsilon, but we could not prove this result. Okay. So let me say that, so I've already flashed this slide. I'm going to say just some very brief things about the argument. The paper is a bit long, so obviously I'll be elliptic here. But what we do know already, this is a previous paper of Ewain Gwynne, Jason Miller, and Scott Sheffield, is that the Tutte embedding and the LQG embedding, they are the same in the limit as epsilon tends to 0. And maybe a very closely related statement is to say that up to parameterization, the random walk converges to Brownian motion. So the fact that you understand the Tutte embedding of this process tells you, if you like, that the random walk on this graph will, in the scaling limit, converge to a Brownian motion if you don't care about the time parameterization. So if you want, what is interesting in our result is only the part that tells you what happens to the time parameterization, which I've explained is this singular change of time using the Liouville clock. Okay, so the argument is divided into 2 pieces. One is tightness and one is characterization. What I think is interesting about these arguments is that they are quite modular. So they are quite independent from one another. They're split up into pieces that I think can be hopefully reused later when there are, more interesting models of planar maps for which we try to prove convergence to Liouville Brownian motion. And so one has to do with tightness, and this is sort of rough control of times. Let's say time it takes for random walk to leave a macroscopic region. So here for tightness, I'm going to try to, I won't say as much for tightness, I hope, as I would for characterization. Anyway, I don't have much time. But what I do want to say is that, you're interested in controlling the time it takes a random walk to leave a given macroscopic region, let's say a ball of radius r. And a priori, one way to control that is to control the moments of the time it takes to do that, to leave this region. And these moments, both the first moment, but also higher moments, they're all given in terms of the discrete Green function, okay? For instance, the first moment is obtained by just summing the Green function, the discrete Green function in the region that you care about. And what you would like to say is that this time is approximately given up to a scaling factor 1 over epsilon, as I said, given by the following random integral. So this is the integral with respect to the mass measure of the continuum Green function. And this is now, the Green function, this ought to be the Green function really for Brownian motion. I mean, you can think maybe it ought to be for Liouville Brownian motion rather than for Brownian motion, but the point is that due to conformal invariance, the Liouville Brownian motion Green function and the Euclidean Brownian motion Green function, they are the same. So when you change the metric, you do not change the Green function. Okay, and so that's why we ought to have here an integral that involves the deterministic green function of Brownian motion here, but integrated with respect to the mass measure of Liouville Brownian motion, if you want. And then, so the main issue to try to prove tightness is to get a uniform control that relates the discrete green function up to constants to the continuum limit, uniformly in X and Y if possible. And, you know, at this point, due to the work of Gwynne, Miller, and Sheffield, we already know that bounded discrete harmonic functions converge to their continuum harmonic functions, to their continuum counterpart. And that's because that's what convergence of random walk to Brownian motion modulo parametrization tells you. And furthermore, they've got some pretty weak estimates on the on-diagonal behavior of this green function. So, you know, that's a very good situation in which to begin. And basically, I won't really say it because of lack of time. But in order to prove these up to constant estimates, what we do is we play with energy estimate and electrical network theory. Basically, you express the green function in terms of electrical resistances, and then you can try to use the Dirichlet principle to try to say that these are obtained by minimizing the Dirichlet energy of certain quantities subject to boundary conditions. And the very nice thing is that you can use functions from the continuum to test, and that gives you bounds on the green function. And if you do that carefully, you get a good control this way on the green function of diagonal, meaning that you have to apply it to points x and y that are separated by some polynomial distance in the Euclidean sense. And then, you know, when x and y are very close, you can still use your naive diagonal bound as well as a priori uniform control for Gaussian multiplicative chaos. So I don't want to get too much into that because it will take too much time to explain. But I think, you know, the idea is that just using electrical network theory, you can try to, and the fact that there is a good embedding a priori that comes with these maps, this LQG embedding, you can get a lot of mileage out of that and get up to constant bounds for the discrete green function. At least if the point x and y are reasonably far apart. Okay, so there is a second part on which I want to say to spend maybe 2 minutes because I'm really out of time. Is that right, Ron?
Yes, but you can take the 2 minutes.
Okay, so I think this is a nice characterization of Liouville Brownian motion. In particular, I hope it will be useful later on when people investigate more models of random walks on planar maps. And the theorem is the following. It says, suppose for every z, I give you a law, pz. So pz will be the law of trajectory of some process starting from z. Roughly speaking, you should think of the semi-group of Liouville Brownian motion, but a priori it's not that. So it can be, it's some trajectory on which eventually will be Liouville Brownian motion. So the important assumption is that we assume that the map which which associates to a point z the trajectory starting from z is continuous in z, continuous in the starting point. And then we make the following assumption. So we assume that we have a Markovian process given h, given, so it's going to be Markovian given the underlying geometry of h, given this random geometry. We assume that this process is a random, possibly random, but in reality it will really be random, time change of Brownian motion starting from z. And the important bit is we assume that it leaves the Liouville measure associated to h invariant. Okay, so you have some field h, which is basically a Gaussian free field, you should think of. And you have a process which you know is Markovian, given h. is a random time change of Brownian motion and leaves Liouville measure invariant. If furthermore you know that the law is continuous as a function of the starting point, then the theorem, the characterization theorem, tells you that there is a constant, a possibly random constant C, such that up to this constant, your process is in fact the same as Liouville Brownian motion starting from Z, associated with this Gaussian free field. So that's the characterization result that we use. As you can see, the characterization result only characterizes the process up to some global linear time change. And that's why fundamentally our result is stated, we're unable to scale time by a factor 1/epsilon. Okay, we would if we could sort of remove the fact that there is some unknown constant C here. So because everything is characterized up to some global constant linear rescaling of time C, we're forced to rescale instead by this median of exit time. And then things are characterized uniquely, basically. I don't know if the characterization statement is clear. There is a very, I think, elegant argument for proving this characterization statement, which uses the notion of a Revue's measure of a Markov process. But because I'm a bit out of time, I think it may be best that I don't discuss that. And instead, I will just stop here and answer your questions if you've got any. So thank you very much for your attention.
So I have a question, can I?
Yes, Ofer.
Yeah. So, but did I understand correctly? It's more testing my understanding than a question. So okay. Your normalization is not random, right? It's a median. So
right, it's an annealed median. Thank you. It's an annealed median.
So in fact, in your theorem, in your general characterization theorem, the constant may be random, but in reality, you prove that it is not in your setup.
Yes, that's right. And
okay,
that's not that takes some work actually.
I can imagine. That's why I asked. Thank you.
Yeah, no, it's okay. It's a very good scale. So you understand the result very well. I confirm.
Nathanaël, I had a question. In your theorem, maybe you can go back to it, just to understand the setup. So you say you do a random walk on G epsilon. So by that, you mean the abstract graph G epsilon, I guess. But then you write linearly interpolated. I guess you meant a simple random walk in continuous time, and linearly interpolated means after embedding?
Yeah, so yeah, sorry, that wasn't very clear. I realized that when I was saying it actually. So it's not very clear the way I say it. Yeah, so first you embed your walk, for instance, using eta, and then you linearly interpolate that. So you...
I see, and it's a random walk in continuous time, say, because you have this and later you say you have, in the statement of the theorem itself, you write eta of x, but x is already linearly interpolated, so...
That's right. So yeah, I mean, we did it in discrete time, but of course there's no difference.
Okay, I see. All right.
Yeah, that's right. So you think of it this way: you do it in discrete time, you embed it using, for instance, SLE or LQG, and then you linearly interpolate that.
Okay, I understand. I had another question.
Yes.
You mentioned at some point that's simple, if I understand correctly, that if you take simple random walk on the UIPT, then you expect that to also converge to the gamma Liouville Brownian motion. Is that correct?
Yes.
Okay, and then just to compare it with last week's talk, last week we heard Matan Zaidel speaking about circle packings in particular, and we know the circle packing of the UIPT. And there, sometimes they don't do a simple random walk, but rather a random walk that makes the walker a martingale. That's a weighted random walk. What would converge to? Is it the same?
I would expect so, yeah. I would expect it to be the same. I thought of the same thing when I saw the talk last week. because I spied
Yes,
to
yes.
prepare for this one.
Very
And,
good, thanks.
it was a very nice talk, actually. And
Yes.
I thought of the same thing. I believe, you know, as soon as your work is embedded in such a way that you know you're going to have a martingale. I don't see what else it could be, but Liouville Brownian motion.
Okay, does anybody else want to ask a question? Please open your microphone and ask, or put it in the chat window.
Yes, Ron. So regarding what you just said about weighted random walk and circle packing, so in fact, Asaf and Daniel Jerison and I have a result that says that this weighted random walk actually the discrete harmonic function in this case convert to the continuous harmonic function.
Oh.
So in a sense, the first part that Nathanaël used is already known for this, and you only need the second.
You mean time change. The only thing that's missing is the time change.
So I will be very interested in learning about this, because that's the sort of crucial ingredients to try to prove convergence to Liouville Brownian motion. But okay, so maybe you can tell me about this result, Ori. I will be very interested to understand what the result says.
Yeah, we can have a discussion with Asaf and Daniel. We can do it even here, but maybe it's not the place.
Okay.
I see, yes, okay, Asaf has a comment in the chat.
Yes. Asaf is commenting that we don't actually know that the circle packing of mated-CRT converted to Liouville Quantum Gravity. Okay, so
right.
and there's another comment which I'm going to ignore.
Okay.
We are not sorry for that, Asaf. We are actually very, very happy.
Okay, anybody else wants to ask a question? Okay, if no more questions, I'll end the recording, but I won't stop the meeting though. If anybody wants to chat with Nathanaël offline, that's fine. So I'm just stopping the recording now, and we'll have it on YouTube later on. Thanks for coming, and we re-meet after Passover in 3 weeks from now.
Yeah, happy Passover.
Thanks, you too.